How are steam locomotives engineered by Nazi Germany in 1943, designed as simplified wartime machines expected to last barely a decade, still hauling thousands of tons of coal every day in Bosnia and Herzegovina more than 80 years later? There are 5 locomotives still in service here, each moving nearly 2,000 tons at a time, built for 50 kilometers per hour, and originally part of a wartime production run of about 7,000 machines, many assembled with forced labor. Their story is a living contradiction, bridging the darkest chapters of 20th century Europe with the modern energy grid of the Balkans. Today, these are among the last commercial steam engines in operation anywhere on Earth, and their survival fuels the heart of Tuzla's coal-fired power supply. This video sets out to unravel exactly how Nazi war machines became the backbone of a contemporary Balkan industry, so subscribe now to follow an investigation into how the legacies of total war still shape the world around us. Nothing about the Class 52 Kriegs locomotive's survival makes sense unless you start with its machinery. Every line of the locomotive's frame, every bolt and axle was shaped by the demands of total war. The 2-10-0 wheel arrangement, meaning 2 leading wheels, 10 driving wheels, and no trailing axle, was not chosen for elegance or speed. It was chosen for traction. 5 coupled driving axles spread the locomotive's weight across the rails, keeping axle loads low, about 15 tons per axle. That meant these engines could run on hastily repaired or lightly built track, exactly what the Eastern Front demanded in 1943. The result was a machine that could pull over 1,000 tons of freight at 65 kilometers per hour, or start heavier loads at lower speeds, all while minimizing track damage and wheel slip. But the Class 52's real trick was simplicity. Wartime shortages forced designers to strip away anything not essential for function and repair. The boiler, built for a working pressure of 16 bar, retained its superheater despite some claims to the contrary because dry, superheated steam improved efficiency and made cold weather starts more reliable. Yet the steam circuit was pared down, the valve gear was simplified, and the number of moving parts was reduced wherever possible. Fewer high-pressure joints meant fewer leaks, and repairs could be done with basic tools, even by crews with minimal training. The steel used in the frame and boiler was not premium alloy, but it was thick, forgiving, and easy to weld or patch in the field. Standardization was another cornerstone. Over 1,200 component part numbers were shared across the entire production run. That meant any Class 52 could be cannibalized to keep another running, a practice that continues in Tuzla today. The interchangeability of key components, from wheel sets to pistons, was a deliberate hedge against chaos. None of these decisions were made with long-term survival in mind. The Reichsbahn's brief was clear: build machines that could be produced quickly, repaired anywhere, and retired after 10 years. Yet these very choices, overbuilt frames, 10 driving wheels, and simplified steam circuits created a locomotive that by accident rather than design could outlast the regime that gave it life. Before considering the moral and historical weight these engines carry, it's their physical endurance, carved into steel and iron, that first demands explanation. Steel shortages and relentless bombing raids forced the Reichsbahn to rethink every stage of locomotive production. The Class 52 frame, boiler, and running gear were shaped not just by engineering, but by a system stretched to its ethical and material limits. Instead of high-grade alloys, most boilers and frames were built from ST47K steel, a tough but unrefined substitute that could be rolled and welded in bulk. The decision to use ST47K was a direct response to the need for rapid, resource-light manufacturing. It meant these locomotives could be produced with less nickel and chromium, metals urgently needed for tanks and aircraft. The result was a machine that could be built by the thousands, even as the war drained Germany's industrial reserves. Production was scattered across more than a dozen factories, from Krupp in Essen to Floridsdorf in Vienna. CKD in Prague, and DWM Posen in occupied Poland. This network was designed for redundancy so that Allied air raids could not halt output entirely. But it also meant that standards varied, and quality depended on what materials and skills were available at each plant. Some sites, like Borsig in Berlin and Maschinenfabrik Esslingen, are documented as having employed forced labor drawn from concentration camps and occupied territories. At DWM Posen, workers included prisoners and coerced civilians, many with no previous experience in heavy industry. Surviving records and survivor testimonies point to harsh conditions, long hours, and a relentless demand for output. Locomotive 33064, built at DWM Posen in 1943, stands as a documented example, almost certainly assembled by forced labor. The use of unskilled, coerced labor introduced inconsistencies in workmanship, but the design's stripped-down simplicity often compensated for uneven skill. The Class 52 was built to be forgiving, with few tight tolerances, minimal precision fits, and thick steel that tolerated patchwork repairs. Yet behind every preserved serial number lies a production story marked by moral compromise. The same choices that made these engines robust enough to survive decades of post-war use also reflect the human cost paid for their existence. What began as an emergency program to keep the war machine moving left behind a legacy that is still in motion today, carrying coal instead of troops, but bound to the same iron logic of necessity. After the war, hundreds of Class 52s left behind by retreating German forces were absorbed into the Yugoslav railways, recoded as JZ-33 series, and scattered across the country's freight corridors. In Bosnia, the Tuzla coal basin became their last redoubt. Here, the logic of survival hinges less on ideology and more on what can be coaxed from steel, sweat, and scarcity. Locomotives arrived with battered frames and mismatched tenders, some bearing the scars of hasty wartime repairs, others rebuilt with welded frames in East German workshops before being shipped south. Tuzla's depot workers quickly learned that longevity was a matter of adaptation. When official spares dried up, machinists began fabricating brake shoes and cylinder pads from scrap metal, welding new firebox sheets by hand. Depot schedules turned into a kind of industrial choreography, 2 locomotives in active rotation, 1 in overhaul, another in light maintenance, and a 5th stripped for parts. This rotation protocol is more than routine. It is the only way to keep the fleet running. As one engine's boiler is condemned, its wheel sets or valve gear are transplanted into another, a process repeated so many times that few Tuzla engines now contain more than half their original parts. Cannibalization is not a last resort. It is a planned, systematic practice built into the depot's daily rhythm. Even the most worn-out units serve as lifelines, their components marked and logged for future use. In-house fabrication fills the gaps left by vanished suppliers. Over time, this self-reliant ecosystem has become as much a part of Tuzla's industrial landscape as the mines themselves. The Class 52s endure not because they were built to last, but because every weakness has been met with hands-on ingenuity and a refusal to let anything go to waste. Every decision to keep a Class 52 in service comes down to money. Tuzla's municipal budget cannot absorb the price of new diesel locomotives, let alone a full fleet replacement. A major overhaul on a steam engine, stripping the boiler, renewing tubes, and remachining wheel sets costs between €100,000 and €300,000, depending on the depth of repairs and local labor rates. By contrast, a new diesel shunter with enough power to move 2,000 tons of lignite carries a price tag between €2 million and €4 million. Even the lowest bids from international suppliers far exceed annual capital allocations earmarked for railway equipment in Bosnia and Herzegovina. For depot managers and city officials, the arithmetic is brutal. Overhauling an existing steam engine can be paid for out of operational budgets, spread over years, and handled by local workshops. A diesel purchase demands foreign currency, international tenders, and a level of upfront investment that simply is not available. Even factoring in the higher day-to-day running costs of steam, coal, water, and more frequent maintenance, the total life cycle expense remains lower as long as the engines can be kept turning over. Spare parts are scavenged or fabricated in-house, and the skills to rebuild a valve or patch a boiler are still present in the workforce. The entire maintenance ecosystem is built around making do with what is on hand. This is not nostalgia or stubbornness. It is a financial equation with only one viable answer. As long as overhauls remain cheaper than replacement, and as long as the depot can stretch each locomotive's life with parts from the dead, the logic of steam will continue to win. The Class 52s are not preserved for history. They survive because, for Tuzla, they are still the most affordable way to keep coal moving from pit to power plant. Today, machines born of forced labor and wartime scarcity power, Bosnia's coal trains, proof that crisis engineering can outlast both ideology and intent. As infrastructure ages worldwide, the line between necessity and legacy blurs. Even history's most temporary solutions can become tomorrow's backbone. Thanks for watching.